Следующий докладчик Nikolay Savinov. So our next speaker is Nikolay Savinov. I think he will be talking English. Nikolay graduated from the PhysTech Department of Fundamental and Applied Physics, and also from mathematics. Then he went also graduated from SHAD. He also worked at Yandex for a year, and for the last 3 years, he's a PhD student at Mark Polyphase group at ETH Zurich, doing wonderful stuff about 3D reconstruction, and we'll see maybe something of the latest.
Thank you very much for the introduction. So, the language of the talk will be English, as Victor already mentioned. And before I actually start with the talk, let me mention. Doesn't work. Let me mention the wonderful people I've been working with. So that's Christian Henne, who's now a researcher at the University of California, Berkeley. Uğur Ladiki, who's a postdoc in our lab, and of course my professor Mark Polyphase, who's now also a director of science at Microsoft Hollands. So without those people, this nice line of work wouldn't be possible. So the talk is going to be about rate potentials for dense semantic reconstruction. So, to just understand the audience, can anybody who worked with 3D reconstruction raise their hands? Oh, there's quite some people. It's very nice. So, first I will actually introduce you to the notion of semantic 3D reconstruction. That's mainly a framework developed in our lab, although there are some other works in other labs. And then I will introduce you to rate potentials and how those potentials could be useful for this kind of reconstruction. So let's get started. So the traditional 3D reconstruction pipeline is depicted here. So you typically start with just the input images, then you run a structure for motion on those images to get the camera poses. Based on those camera poses, you estimate depth maps. That's kind of the stuff the previous speaker was talking about. Then those depth maps could be fused into the volume. What do I mean by that? You split the volume into small volumetric cells, like cubes, they're called voxels, and you label each voxel as being inside or outside the object. So the result is basically labeling of this volume into 0 or 1. And you can extract the surface, for example, you can extract this building from this labeling. But with the standard pipeline you can see some problems. For example, you can actually see at this reconstruction that's a standard TV flux fusion, that's kind of standard algorithm for doing that. So you can actually see that the ground is missing, and the building, you can see there at the top that the part is also missing. So to solve these problems, and this is, just to clarify, this is a very serious problem. When you try to reconstruct, you go outside, you take images, you want to reconstruct a nice scene, and maybe you want to do some augmented reality there, you want to put some monsters for whatever computer game you like. This is a serious problem because if there is a hole, on the floor, the monster is going to drop there, and there won't be any nice game. So this problem it is really a big problem of 3D reconstruction, a big unsolved problem. So to solve this problem and to get some more information about the actual objects in the scene, people started to extend this approach to multiple labels. So before we were talking only inside or outside the object. Here we go to multiple semantic classes. For example, here it could be a building class or vegetation class or some ground class. So where do those classes come from? So we basically run a semantic segmentation on the input images. So this semantic segmentation could come from any classifier you like. This could be CNN or this could be some random forest, doesn't matter. We take this already as the input data to our method. So what people typically do, what was the starting point? So people basically were taking this reconstruction which you see at the top, like from the traditional pipeline. Then they were also taking those semantic segmentations, and they were reprojecting those semantic segmentations onto the surface. So basically you just paint the surface with those colors which represent semantic classes. But of course this doesn't solve the problem with the missing ground. You can see the result at the right bottom corner. Also, one other problem is that when you try to paint the surface, you actually don't know where the transition is between the classes, because here you see it. So this is like the tree, and this is the building, but where the transition is, you have absolutely no clue. In our line of work, and that is the framework developed in our lab, we are doing a completely different thing. So we want to fuse all this information, those depth maps and the semantic class likelihoods, we want to fuse them jointly in the volume. So again, you split the volume into those voxels, and to each voxel you want to assign a semantic label of the class in this voxel. For example, if you are inside the building, even if you don't observe this part, you want to label it as building. Now the nice thing is that if you do it jointly, your geometry estimates, which come from the depth maps, and your semantic estimates, which come from the segmentation, they can actually help each other. One crucial component of this reconstruction is also using the prior knowledge. So for example, you know that the ground is preferred to be horizontal, that's normal, right? And the walls of the building are preferred to be vertical. So of course you don't want to encode this as a strict constraint, like make it like z equals 0 plane. That's not going to work because in practice that's the real world, right? But you want to have this preference which you ideally learned from the real data. So this is this continuous surface penalization part. So in our framework, this preference for horizontal ground or vertical walls or some other preference is coded as a regularizer. But this is a part of prior work. So I will not talk about this part here. Now, one other nice thing which happens if you actually do labeling of the volume is that you can directly get semantic labels separated in 3D. So, although you don't really observe where the transition is from your input data, because of your prior, preference for example, ground to be horizontal, you can actually extract that this was part of the volume which was building, and this is the part of the volume which was the ground, because you know that the building is standing on the ground, right? Also, you can separate, as you can see here, you can separate the building from the vegetation, because you kind of prefer the building walls to be vertical. And this is just not possible if you do what I mentioned before with painting. You can actually observe nice difference, because once you turn into this framework, you can actually see that you get the ground back. And that is important. Now, this is just the introduction to the topic. This is the introduction to the framework which was developed in our lab, and now I'm actually getting to the contribution of this work. So as I said, the smoothness was actually already developed in the prior work, and here we're going to talk about the data term. So what is actually the input data? So the input data comes in two forms, as I already mentioned. You can see it on the left. So on top you see the depth map, and at the bottom you actually see the semantic segmentation. Now, on the right, you actually see the 3D solution. So this is a labeled volume. Every voxel is labeled into, building or vegetation or ground. Now, in the middle, you see the projection of this solution onto the camera plane. So please notice that the left column is actually, it corresponds to some particular camera position. So if you take some solution, you can project this solution onto the camera position to actually get the depth map from the solution and the semantic segmentation as the first visible label along the ray. So now the data term which you want to achieve is something which prefers these two things to be similar and these things to be similar. So the middle column should be similar to the left column, and at the same time you strive for a solution which is smooth in 3D. So what you see on the right should look smooth, so there should not be some noise speckles flying in the air. Now, how to actually implement this ideal data term I was talking about, this preference for those images to be similar. So the important thing to notice is that when you actually have an input image, it contains the information about the whole array in 3D. So basically here you see the depth map, and this depth map tells you what's the distance to the closest object. Of course, the depth map is not ideal because it's estimated from just the images, so it's a noisy depth map. So you might have an outliers. So here you actually need to take into account all the variables along the ray. You remember each voxel has its own label. Label corresponds to a variable. And ideally, all the variables along the ray are linked because otherwise you can't handle visibility. For example, you want to prefer something to some transition from free space to occupied to be here, but if it was occluded before by some other class, you just say that it's outlier. Now, what people typically do is they approximate these complicated high-order potentials with a simple function. And this is called unary potential. So this is basically you put a linear function with some weight into each volumetric cell. Now, this approach is not ideal because it leads to two kinds of artifacts. I listed those artifacts at the bottom. So one of them is closing some, for example, arches in the buildings. So even if you observe something in the arch and you have some data, like some depth estimate inside the arch, which is, let's say, far away, it is still not covered by unary potentials because you see the spread of this evidence is limited because you forget about the whole ray and you just put it into a small window in 3D. Now, another problem is inflating of the ridges. For example, look at this roof. This is the algorithm which also does reconstruction with unary potentials, and you can see that it's wrongly inflated. Now, what we do in this work, we really do high-order ray potentials, which help to resolve those problems. So this is done with ray potentials and this one as well, and you can actually see that the reconstruction improves. Now, how do we actually formulate and solve this problem? So here I just give a high-order overview of what kind of problems we are solving. So the easiest way would be to formulate it as a discrete optimization problem, and then we could actually solve a convex relaxation of this problem. Of course, convex is nice because you can find a unique solution easily. But the problem is when you relax the problem, that means you basically had variables which are either 0 or 1, then you relax it, you get the whole interval from 0 to 1. And the problem might be that you can't really round this relaxation. For example, if you get 1/2 everywhere, you don't know if you want to round it to 0 or to 1. It's kind of in between. And as you will see, that's exactly the problem which will happen with this convex relaxation. So this is the actual naive convex relaxation formulation. So all this looks pretty complicated, but just you need to understand kind of the shape of the optimization problem. So here you see the actual objective. We do minimization of variables x and y. Here you see it consists of two parts. One is a convex regularizer, as I mentioned before. We will not talk about it, it's prior work. This is basically your preference for horizontal, ground and vertical walls. All you need to know is that it's a convex function. And what about the rest? So here there's a linear function, and here are the linear constraints. So if you leave out the convex regularizer, the rest of the problem is just a linear program. Now, what do those variables mean? So basically, x is an indicator if voxel is occupied with some particular label L. So you see there is a double indexing. S means spatial position in the volume, and L means label. The relaxation is indicated by having it from 0 to 1. So obviously, only one variable should be assigned to each voxel. So this is implemented as this summation. So at most it should be 1. And there is exactly one variable assigned. So anyway, so there are y variables which correspond to taking profit in the objective, and there is those x variables which correspond to the actual solution in the 3D space. Now, let's see what do we want to achieve. So here is a reconstruction of some 11 line on the table. So that's a very simple test data set, but it's like a real data. And what you want to achieve is this. So what is this? It's basically a slice through the 3D volume. So there are only two labels here. You know, traditional reconstruction is a subset of semantic reconstruction. Just use two labels, inside and outside. So this is a slice through the solution volume, and what you want to have is basically, you know, free space label assigned here and occupied label assigned here. And maybe it's a bit non-binary on the boundary, but that's fine. Now, what you actually get if you run this optimization problem is this. So this is a big problem because it's exactly one half. And that is the case which I mentioned before. That's the most problematic case. You don't know where to round it. Do you round it up or down? Either way, it's going to be either free space or all occupied, and that's completely unacceptable. Now this is the most important point of this talk. So if you want to understand this talk, then you should concentrate now and try to do it. And to help you, I actually give you a simple example. So this example consists of just one ray. This ray has 3 positions. So basically, you can imagine volume which consists of 3 volumetric cells. And you want to assign the first transition from free space to occupied space, because you know that's the first feasible transition. Now, from your data, you have the evidence. If you put this transition to the very first cell, which has index 0, you get -2. If you put it to the cell 1, you get -3. And to the last one, you get -2. Now, these are just some constraints which are necessary to have consistency between the x solution and the y variables. Now, I have a question for the audience. If you were the algorithm, what kind of solution would you assign? Where would you put that observable transition from free space to occupied space? So you have 3 options, and you get some profit. So since you minimize, you want to get as much negative as you can. Obviously, you can't assign you know, transition everywhere. So you need to choose one position. Can anybody tell me what position would he or she choose? Y1? Right, so that was kind of easy. So Now let's look at this solution. This is something which you would expect when you formulated this optimization problem, because that makes sense. You know, there's no regularizer, you just assign it to the most probable position. This solution, it's listed here. You can check that, you know, all the inequalities are satisfied. And this solution has cost -3. Now, that's the most important part of my talk today. Look at this solution. So all the variables which you see in this formulation are assigned 1/2. You can check that all the constraints are satisfied because those are done, those are as well, and those, and those, and those. They are all satisfied. Now let's look at the cost. It's -3.5. And this is very important because it has a better cost than the reasonable solution which you would expect when you formulated the problem. So you see that the formulation actually cheats and it tries to put the transition, this surface, everywhere to profit from all the scoring positions. And when we discovered this problem, we spent quite some time understanding how to fix it. What we came up with is we need to add some special non-convex constraint, which allows for, you know, cutting out this bad solution from the feasible set. This constraint turns out to be efficiently solvable in practice, as I'll explain later. Just to give you an intuition what this constraint means, this is on the left. You see the global view, those x variables, those indicators. On the right, you see y variables. Y variables are specified for each particular view. So you want to enforce some kind of consistency between x and y. Now, look at this constraint. This constraint actually helps to enforce this consistency. If you try to insert this 1/2 solution with this constraint, it's not going to work. Simply because there is 1/2 here, 1/2 here, and it turns into 0. And now you can't take 1/2 for this y variable. So we cut it out. And this solution is not possible anymore. Now, just a few technical properties. So it can be generalized to multi-label because this one was given for just two-label problem. It's optimizable. I won't go into detail how to do it, but we did it in the paper. And there are some mathematical properties which hold for this constraint. So you can actually prove something. Now, just quickly the results of our method. So here you can see that for our method, the pillars, please pay attention there, the pillars are correctly thin, but for the previous work they are inflated. So this is kind of effect I was talking about in the introduction. There is this fattening effect. So we get rid of it. Now this is a bit unexpected, so since there are no benchmarks for semantic reconstruction, we ran it on a standard multi-view stereo benchmark, and suddenly we got directly to the first place on some of the data sets. So you can actually see that by solving the visibility problem properly using this constraint which we introduced, you can actually get state-of-the-art results in the 3D reconstruction task. You can check more results on the benchmark website. This is basically a screenshot from there. Now, one very interesting property is that our algorithm is particularly well suited for reconstructing thin objects. So this is a well-known problem in 3D reconstruction. Simply because when you observe the surface from opposite directions, your unary potentials cancel out. Just to remind you, unary potentials are simply linear functions, like linear weights you put into each voxel. When you sum up minus with plus, you get 0. And with our method, there is no such problem because you don't say where the occupied space and where free space is, you just say that the surface should be somewhere in the uncertainty window. So now, during the CVPR, there were some companies who came by and asked how this algorithm works, how it should be applied in practice. So here I just give a few of my recommendations. So first of all, the algorithm is at this point is pretty slow, so you shouldn't run it for the whole scenes you want to reconstruct. My recommendation is just to pick sub-blocks which need to reconstruct properly. For example, that could be some banner or some thin surface or some statue with lots of details, and just run it there. Run it where you actually need accurate reconstruction, not everywhere. Now, this is close to the conclusion of my talk. I would like to take a minute to advertise the other research I've done in the lab recently. So these are two papers. So the first one is called TI pooling, and it's on enforcing invariance directly in the architecture of the deep neural network. And the bottom one is called quad networks. It's a new approach to unsupervised discovery of sparse representation of the data, like interest points. So that concludes my talk. Thank you very much.
Thank you. So your formulation of objects is voxels, right?
Yeah, exactly.
And does it require a lot of voxels in practice to represent a lot of objects? Isn't that a computational problem or like memory problem, or is there maybe some interesting compressed representation, octrees or something like that?
So basically, octrees could be applied in this case. We haven't tried them. One other option is to use tetrafibrilization of the space. That's also possible, and one of my master students is working on it. So, to answer your question, yes, it is a problem, and there are some standard ways to solve it.
The characterization is this creating mesh object of voxels?
It is basically you run delta tetrafibrilization on the space of 3 points, which you get from the depth maps.
So it's like a convex Hall problem in 3D.
Well, it's you need to split the space of points into the tetrahedrons. That's basically what's happening.
Thank you.
That was the first one.
So what do you use as inference method at the end of the day?
I don't hear, sorry.
What do you use as inference method in the end?
So for solving the
Then you
optimization
have
problem,
combinatorial optimization problem with your potentials. So you have to, what do you use to solve that?
so when you relax it, it turns into convex programming, and we use primal dual first order algorithm.
So you don't solve actual problem with discrete optimization. You only do relaxations.
Yes, but I didn't have enough time to mention, but actually the solution has some approximation guarantees in some special cases.
Is the quality of input images is crucial for your algorithm?
So this is a kind of algorithm which is one of the most accurate in the world. So yes, it is crucial, but it can probably do better than many other algorithms. And you can actually, I guess you can see more difference with bad images with respect to other algorithms than with good images.
Thank you.